In this video, we're going to be talking about the periodic table trend of reactivity. And to understand this concept, it's going to be very important that we watch through the previous videos. Specifically, it'll be very important to understand the trend for valence electrons, which you'll just look at the column number to determine the number of valence electrons. So column 1 has 1 valence electrons. Elements in column 5 have 5 valence electrons, etc. Next, ionization energy will be very important to determine if something's going to react. It'll have a big influence on the reactivity of elements, as will electronegativity. And we'll talk about why here in just a second. But reactivity of elements, let's first look through our definitions of what is a chemical reaction. Well, we have our more technical examples are going to be these first two, and I still try to simplify the language so that we understand it. But a chemical reaction is the chemical transformation from one substance of something from one substance to into another. Or we could say, in a little bit more simple terms, anytime bonds are being formed or broken. But we haven't learned about chemical bonds yet, so we're going to have a very, very simplified definition of the gaining or losing of electrons. That definition is not really that's not a very technical or completely true definition, but it's going to serve us really well for today's lesson in introducing the topic of reactivity of elements. Once we start talking about chemical reactions and bonds being formed and broken, we can start maybe using one of these other definitions. But for today, this is the definition we will be using. So, looking at the periodic table, we said that the purpose, and actually the previous video, we talked about charges that elements tend to form when they form ions. And the purpose of forming these ions, of gaining or losing electrons, was so that they could get to 8 valence electrons. That's their entire purpose in life. They're not really living, but that's their purpose in life, is to get to 8 valence electrons. And so the gaining or losing of electrons, the purpose of that is to get to 8. So these elements right here are the ones they already have 8, and every other element is trying to get to 8. So the gaining or losing of electrons. So looking at the periodic table, let's find the 2 columns of elements that are going to be most tempted to get to 8. They're going to be the ones that are closest to 8. So pause the video and think about which elements those might be. Which elements are closest to 8 to where they are very antsy, very ready to get to 8 because they're almost there. I would say that these elements right here are very close to having 8 valence electrons, as are these elements right here. And with a couple exceptions, hydrogen, it only wants 2, same thing with lithium, and etc. But we're not going to talk about the exceptions so much. But which elements are, if I want to use general terms that apply to all of these, which elements are very close to having a full valence shell? And so we would say group 1 elements and group 7 elements, these halogens right here. So of all elements of every single element on the periodic table, the elements in these 2 columns, here and here, they are the most reactive elements on the periodic table. Does anybody recall what the least reactive elements on the periodic table are? Well, in our last video, we had mentioned that these elements here, the noble gases, those are the least reactive elements on the periodic table. And why might that be? Well, they already have 8 valence electrons, and the entire purpose of any kind of chemical reaction is to get to 8 valence electrons. And so if they already have that, then they have no point in reacting. There's no point in them reacting, so they're not going to react. They don't react. But these other columns here that I I'm going to go ahead and highlight instead of circling. But these other columns, I'm going to do one in blue. This column right here, these halogens, they are some of the most reactive elements. And then also these elements in green here, they are some of the other most reactive elements on the periodic table. Why are they so reactive? Well, let's look at our elements here, these halogens. Why are they so reactive? Well, they are just one electron away from getting to 8 valence electrons. So fluorine, for example, right here, fluorine has 7 valence electrons. If it just gets one more electron, here's an electron right there. If it just accepts one more electron, well, now it has 8 valence electrons. So that's why it's so reactive. It just needs one more, so it's going to react very heavily so that it can get that one more. These elements here on the left, they are also one away from getting 8 valence electrons, but instead of gaining an electron, they want to lose an electron. So sodium, for example, it has 1 electron in its valence shell. So the easiest way for it to get to 8 valence electrons is going to be to erase this valence shell. And now, voila, it has 8 valence electrons. So that's why these two columns are the most reactive columns on the periodic table. Let's dive a little bit deeper and see, of these columns, which elements within these columns are the most reactive. So let's start with these over here on the left. So which elements of these group 1 elements, the column 1 elements, which ones of these are the most reactive? Well, let's think about the different trends we've gone through so far. We said that ionization energy is going to be pretty important and electronegativity are going to be pretty important. Those are going to be the 2 important factors for determining whether these elements are going to be, which of these elements in the columns are going to be most reactive. So let's think about what these elements are trying to accomplish in order to get to 8 valence electrons. They want to lose an electron. So that's going to be talking about our concept of ionization energy. Which we recall is the amount of energy required to remove an electron. All right, ionization energy is the amount of energy required to remove an electron. And we said that these group 1 elements, they want to remove an electron so that they can get to 8. And so we want to find something that is going to be very easy to remove an electron. So think back through that video, pause here, and think about which elements in this column are going to be the most likely to lose an electron, or the easiest to lose an electron. So is the trend going to be to where it's easier to lose an electron as we go down or as we go up? Which is easier to lose an electron? Well, ionization energy, again, is the amount of energy required to remove an electron. And so high ionization energy means it requires a lot of energy to remove an electron. And low ionization energy means it does not require very much energy to remove an electron. And so we want to go for something that has low energy to remove an electron. It does not take very much energy to remove an electron. And the amount of energy required to remove an electron is going to be very correlated with the size of the atom. Look at sodium here. It has these outer electrons, they're in the 3rd energy level. So they're not too far from the nucleus. There's still a decent attracting force between the nucleus and that electron. There's also not very much electron shielding. It only has 2 layers of electrons shielding it from the nucleus. But if I compare that to francium down here, francium has 7 electron shells. So this electron right here is pretty darn far from the nucleus. So that is not going to help things. It's pretty far from the nucleus, so the attracting force between that electron and the nucleus is pretty weak to begin with. Plus, we have 6 layers of electrons shielding that electron from being attracted to the nucleus. So that's going to further reduce the force that the nucleus has in pulling that electron towards it and holding it in place. So this electron, it is not going to take very much energy to kick it out and remove it. So we're going to say that for these column 1 elements, the trend is that reactivity is going to increase as we go down. Next, let's look at these column 7 elements, these group 7 elements. So group 7 elements, do they want to gain or lose an electron? Well, they are 1 away from getting 8 valence electrons because they have 7 in the valence shell. So fluorine, for example, has 7 electrons in the valence shell, as does every other element in that group. And so are they wanting to get rid of an electron like these elements over here? Or do they want to add an electron? Well, they're going to want to add an electron. So ionization energy is not going to, they're not going to try to find something that has low ionization energies to where they can easily remove an electron. Because if they easily remove an electron, that's not going to help things. They want to gain an electron, not lose an electron. So it's going to be the opposite for them. They want to gain an electron, so they want to attract electrons. So let's think to our definition of electronegativity. And electronegativity in simple terms is the tendency to attract electrons. Tendency, might have spelled that wrong, to attract electrons. So they want to gain an electron, so therefore they want to attract electrons. So whatever element is going to attract electrons the most is going to be the element that is going to be the most likely to react. So think back to our periodic table trends for the trend for electronegativity, and which of these elements has the highest electronegativity? Well, electronegativity is going to increase as we go up and to the right. So it's going to, for these elements, it's going to increase as we go up. So for group 7 elements, the reactivity is going to increase as we go up. So fluorine is the most electronegative atom or element on the entire periodic table. So it is the most reactive of the group 7 elements, the halogens. Whereas these elements down here located on the bottom, they are not as reactive because they have lower electronegativity values. They attract electrons less so than fluorine and chlorine and bromine up here. So electronegativity is the driving force here. They want to attract electrons, and if they're able to attract an electron and form a bond or create this chemical reaction from attracting electrons, then they are going to react. And if they react, that's what we're looking at here, reactivity. So again, to recap, these elements here on the left, reactivity is, first of all, the elements on the far left, the group 1 elements and group 7 elements, are going to be the most reactive elements. Within these 2 columns, Group 1, reactivity is going to increase as we go down because it's easier to remove an electron, and that's their goal, is to remove an electron. And for these elements here on the right, they want to gain an electron. And in order to gain an electron, it's going to be important that they have a high attraction for electrons. So if they have a high attraction for electrons, they're more likely to gain an electron. And if they gain an electron, then they cause a chemical reaction and are therefore more reactive. Hopefully that's helpful. Let me know if we have any questions.